Good morning, guys. It's 10 a.m., so I think I'll make a start now. So today's session is we're doing A-level chemistry today, and we're going to be focusing predominantly on rates of reaction, and I'm going to talk a little bit about equilibrium at the end of this session. It's nice to see some people from yesterday as well that have been joining. Okay, so a little bit of a timetable as to how the day is going to work. So this session runs from 10 until 2. Our first block will be on orders and rate equations until 10:45, and we'll have a break. Then rate graphs, we'll have a break for lunch. Multi-step reactions and the Arrhenius equation, a break, equilibria, and then a little clinical skills corner at the end, just to relate it a little bit more to medicine. So, and then what about me? My name's Caitlin. I'm a third-year medical student at the University of Sheffield. And, you know, a fun fact about me, in my spare time, I love to play badminton and go hiking. Anything outdoorsy, really, I really enjoy. So how does this session work? So I'm going to kind of go through it all with you and teach it. If you have any questions, just simply ask in the chat and direct those questions to Ask Ace. They are another doctor who's helping me out today, and they will answer any questions that you have. We're also going to do a little bit of exam practice. There'll be a few exam questions dotted in as we're going. And this session is also recorded, so you guys can watch it back at the end if you need to clarify anything or have any questions. There'll also be questions like this as we go through, and they'll be in this format. We're using the Zoom polls, so it should be fairly self-explanatory as to how you can vote on these questions. Okay, so what we're going to talk about today: orders, rate equations and rate constants, rate graphs, rate determining steps, effect of temperature on rate constant, equilibrium constants. So yeah, those are the things we're going to be talking about today. And so hopefully you guys will be a little bit more prepared when you learn about this in your A-level chemistry lessons. So I'll begin. So first of all, we're going to start by talking about rate of reaction. So what is a rate of reaction? First of all, that's what we want to talk about. Well, the rate of reaction is measured by observing the changes in quantities of either reactants or products over a certain time frame. So I'll give you an example. You might have seen in lessons, you have a conical flask. Oh, very dodgy drawing of conical flask with some kind of acid in it, probably hydrochloric acid, and some calcium carbonate chips. And when you put the calcium carbonate chips in, this gives off a gas. And we are able to measure the rate of this reaction over time. So we use this equation to measure the rate of reaction. So what we need to do is we either measure the quantity reacted. So for example, we'll measure how much calcium carbonate, how many grams of calcium carbonate, say for example, have been used, or we'll measure the amount of product produced over the course of time. So if we're saying that this reaction produces CO2 gas, then we can also try and measure that. So I've just got a little question for you guys to start off with. If you direct your answers to me in the chat. Quantity can be measured in a lot of different forms. Can you name some examples of forms that we can measure quantity in? And what do you think is the most appropriate? So I'll give you a few minutes. If you just type your answers in the chat, just anything you're thinking really, there's no right or wrong. Don't be afraid to ask any questions. Yeah, we've got centimeters cubed. Yeah, brilliant. We'd use that if we were measuring a volume. We got any other ideas of what we could measure things in? Grams, yep, brilliant. Yeah, those are all good ways of measuring the rate of reaction. However, there's one particular one that chemists really like to use. So I'm now just going to start with a question. So what do you think? What unit do you think that chemists like to use to measure the rate of reaction? Okay, just launch the poll. If you guys could vote, which one do you think it is? It's kind of a little bit obvious from the way it's formatted. I think I'm just waiting on one more answer. Oh, there we go. Got them all. Yep, brilliant. Well done. I mean, it was very obvious from the fact that this is in a different font. Oops. In a different font to before. But yeah, so chemists like to measure rate in moles per dm3, moles to dm minus 3, seconds to the minus 1. These other units, minutes, would just simply be measuring, you'd just be measuring the time, not the rate. Milliliters per second, again, is an idea, but we don't, it's not quite as accurate as this one. And kilograms per minute, the same again, it's just not as accurate as moles, dm3 to seconds to the minus 1. So, for consistency's sake, chemists like to measure rates of reaction as a change in concentration with time. And that's what we meant with the, that's what we saw when we saw that equation. So will it pop up again here? Here we are. So rate is change in concentration over change in time. So I'm sure you'll have learned from A-level chemistry, we like to measure concentration in moles, dm minus 3, and we measure time in seconds. So you might be a little bit confused as to why is it seconds to the minus 1? Well, if we're saying that rate is change in concentration, which is moles per dm3, divided by seconds to the minus 1, in order to get rid of this divide sign, we need to bring the seconds to the top. And to do that, you times it by minus 1. So we end up with this unit. Moles to the dm minus 3, seconds to the minus 1. And that is what we measure the rate of reaction in. So now we've measured the rate of our reaction. We know that when we're using our conical flask with our calcium carbonate chips in and hydrochloric acid, and it's giving off this CO2. We're measuring the rate of this reaction. So what we do is we measure the volume of gas that is being produced, and we can convert that into concentration because we know that moles equals volume times concentration. So we can measure, we're able to find out the concentration by simply calculating the volume and knowing how many moles that is. Okay. So we're now going to talk about these things called orders of reaction. So you'll know that all reactions happen at a different rate. You'll have seen that in real life. I'm sure a lot of you will have seen a really good example is if you have a bottle of Coke and you put some Mentos into it. A lot of you will have seen this reaction and you know that it explodes and gives off loads of CO2 gas, loads of bubbles, and it explodes. But changing the concentration will often change the rate of this reaction. So for example, if I put more Mentos into my bottle of Coke, then this reaction will go quicker. It'll react faster. But chemists don't like the unknown. They like to know how much faster that this reaction is going to take place. And we're able to predict that by using things called orders of reaction. So The rate of reaction of something, so the speed that CO2 gas is being produced in my calcium carbonate and hydrochloric acid reaction is proportional to the concentration of the reactant raised to a power. So it's proportional to the concentration of this reactant. If I had a higher concentration of hydrochloric acid, the reaction would go faster. If I had a lower concentration of hydrochloric acid, the reaction would go slower. And that is because these things are proportional to one another. And it's raised to a power. And we write this like so. So rate is proportional to A, which is our reactant, to the power N, which is the power. So N tells us how much faster the rate is going to be as you increase the concentration. And for each reaction, whatever number N is, we call that the order of the reaction. So, yep, we've just said that for each reactant, the power is the order of reaction for that reactant. In a reaction, different reactants can have different orders. So if I pop an example up here, if say A is hydrochloric acid, and we raise it, say, to the power 1. No, that is supposed to be a 1. Raise it to the power 1. Say we have a concentration of hydrochloric acid of 4. 4 to the power 1 equals 4. Okay, so as the rate is multiplied by 4, or as the concentration, sorry, is multiplied by 4, the rate will also be multiplied by 4. That's what that 1 up there means. However, if hydrochloric acid had a 2 there instead of a 1, 4 to the power 2 equals 8. So if we increased our concentration by 4, because they're directly proportional to one another, our rate would increase by 8 because of this power. Okay. And in a reaction, there's not always just one reactant that has an order that affects the rate. There might be multiple. And different reactants can have different orders. And they affect the rate in different ways. So some common orders, the ones that you guys will learn about, are 0 order, 1st order, and 2nd order. So you can have things to the power 0, stuff to the power 1, and things to the power 2. If something is to the power 0, say my concentration, again, of A, hydrochloric acid, is multiplied by 4. But the 4 is to the power 0. We know from maths that anything to the power 0 equals 1. So no matter what the concentration, even if we timesed it, even if the concentration was multiplied by 10, anything to the power 0 is always 1. So this means that it's not going to change the rate of reaction at all. This will not alter the rate of reaction because it's always the same number and it always stays at 1. Okay, and so this is what is being explained in here. I'll just go through it again so you guys, to make sure you guys definitely understand. Anything to the power of 0 will always be 1. So when our rate is proportional to our concentration, and the concentration is to the power 0, then no matter what the concentration of A, it will always be 1. So however much you change the concentration of this reactant, it doesn't have any effect on the rate. Okay. So yeah, and here are just some examples of it. Even if you had a concentration of 999, anything to the power 0 is always 1. So now we'll move on to first order reactions. So a first order reaction is what I mentioned before. It's when the concentration is to the power of 1. So this means that when I double the concentration, so I'll times the concentration by 2, the rate will also multiply by 2, because anything to the power 1 is always itself. 2 to the power 1 is equal to 2. So say my concentration of A was 10, we multiplied it by 10, then our rate would also be multiplied by 10. It's as simple as that. Yeah. Anything to the power of 1 is just the same. So if the concentration of A is doubled, the reaction rate is doubled. If the concentration of A is tripled, the reaction rate is also tripled. So if we look at this experimentally, we'll go back to a conical flask and with our calcium carbonate chips and hydrochloric acid. If we have, instead of 3 calcium carbonate chips, we have 6. So we've doubled the concentration of our reactant, which is a calcium carbonate chips. We will then double the rate of reaction. So this CO2 that's coming off here, the rate which that is coming off will be double, times by 2, compared to what it was with only 3 calcium carbonate chips. Now, second order, it's the same theory, but now our concentration of our reactant A is to the power 2. So we have, I'll go back to our marble chips again, our calcium carbonate chips, sorry. So I have them in here with our hydrochloric acid. So I'm now going to double the number of calcium carbonate chips. So we've now got 4 instead of 2. So we've doubled A, but 2 to the power 2 equals 4. So the rate is going to be multiplied by 4. Concentration times 2 is rate times by 4. So we've got 4 times, the rate is going to be 4 times faster when I double the concentration of the calcium carbonate chips, okay, compared to before. And the same works whether A is tripled. So if the concentration of A is multiplied by 3, then our reaction rate is 3 squared, which equals 9. So hopefully that makes sense, and we'll put it into practice in a moment. So now I've got a question. So if my concentration of a first order reactant, so that's to the power of 1, is doubled, what effect is there on the rate? So I've shown it you as a little diagram here. So it's 2 to the power 1 is what we're looking at. What is the effect on the rate? I'll just relaunch the poll. Okay. Got one more answer. Okay, so there we go. We've got 3 answers for B and 1 for C. So I'll go through my my working out of this one. The wording is a little bit difficult, I know. So I've included the little diagram here. So if we write out the equation, rate is proportional to, so my concentration of my first order reactant is doubled. So I'm going to put the 2 in brackets here. And then I've said it's first order, so it's to the power of 1. So 2 to the power of 1 is equal to 2. So when my concentration is times by 2, because it's to the power of 1, my rate will also be times by 2. So the answer to this one is B. C would occur if it was a second order reaction, and A would be true if it was a 0 order reaction. Okay, so now I've got another one, a little bit more, slightly more difficult, still along the same lines though. If my concentration of a second order reactant is multiplied by 5, what effect is there on the rate? So for this one, we're saying that the concentration, we're saying that the concentration that our reactant is being times by 5, and it's a second order reactant. Yeah, so it's to the power of 2. I'll just put the poll up now. Yeah. Yeah, perfect, straight away. I think you guys have got that now. So all correct, it is indeed, would indeed be multiplied by 25, and that's because 5 squared is 25. Well done, guys. I think we've got that. So now we're going to put what we've just learned into a rate equation. So why do we need to know the orders of reactants? And why do we need a rate equation? So the rate equation gives us the mathematical relationship between the concentrations of the reactants and the reaction rate. So for 2 reactants, A and B, the rate equation is shown below. So if you imagine it's A plus B makes C plus D. Okay, so if we have the 2 reactants A and B, we pop them in square brackets there. It is once again proportional to the rate, but now we have to add in this funny constant K. As most of you will know, probably from doing A-level maths, when something is proportional, so before we said that the rate was proportional to the concentration of A, the power M, and B, excuse my messy writing, we said it was proportional. Well, in order to get rid of this proportionality sign, we need to put a constant in. So we're now saying that rate is equal to K, which is a constant, and then we have the concentration of reactant A to whatever power that is, and the concentration of reactant B to whatever power that is. And so the reason we need to find out what K is K allows us to calculate an unknown value. So if we imagine, say we know the rate, we know K, we know the rate, we know the concentration of A, we know the orders of both of them, but we don't know what concentration of B we started with. Well, it means we can rearrange this equation and we can figure out our unknown of B when we know what K is. So it's really useful for us to be able to figure out K. Yep, so as I said, it's the rate constant or the proportionality constant. It mathematically converts between the rate of reaction and the concentrations and orders of each reaction. Yeah, these are just the labels which I mentioned earlier. So if you noticed in the last slide, we had more than one reactant. and we had more than one reactant and they both had different orders. So we can also work out the overall order. So the overall order of reaction gives us the overall effect of the concentrations on all of the reactants on the rate of reaction. Okay, so say for example I'll pop this down here. Say for example we doubled both A and B, then if we know what the overall order is, say for example M is 1 and N is 1, we know that the rate is going to be quadrupled because it's to the power 2 overall. Our overall order is 2, if you see what I mean. So to figure out the overall order, all you simply do is you add together the individual orders. So if A was to the power 1 and then B was to the power 2, our overall order would be 1 plus 2, which equals 3. Okay, so that's all that bit is. So the orders, is there a question coming here? What is the overall order for this reaction? Can you guys pop in the chat if A is 0 order, B is first order, and C is second order, what is the overall order of this reaction? 3. Yep, brilliant. You've got it. You've all got it. Perfect. So it's just as simple as that. That's the overall order. Then we can now write the rate equation. So for this one, our rate equation, when A is 0 order, B is first order, and C is second order, we'll write it down like that. However, scientists, because A isn't affecting the rate of reaction at all, we tend to just omit A from the rate equation. If anything is to the power 0, it will always equal 1. So we do tend to just omit it from the rate equation. So we end up with our final rate equation being B, which is to the power 1, and C to the power 2. Okay. So now we can figure out the units of the rate constant. So the units of the rate constant change depending on the equation. It changes depending on the order of the equation. So let's skip on. So what you need to do, you need to rearrange the equation and make K the subject. So we have this equation here. Rate equals K, and then concentration of A to the power 1. So if we rearrange to make K the subject of this reaction, we want to divide everything by A to the power 1. So we have K equals rate over A to the power 1. Like so. Oh, they've already written that there for me. And then if we now want to substitute our units in. So we've said that rate is measured in moles per dm3 seconds to the -1, and concentration is measured in moles per dm3. So what we can do is we write it out like this. Now, because we have 2 lots of moles per dm3, these can be cancelled out because they're on the same sides there. So we're just left with K is equal to seconds to the -1. Okay. That's how we work out the units. The units are really important. Often they'll get you a mark in the exam. There will just be 1 mark for working out the correct units because they know it's something that often trips people up. Okay, so it gets a little bit more difficult when we start having powers in our rate equation. So what would be the units of our rate below? I'll show this one as an example. So we're making K the subject again. So dividing everything by A squared over B, A squared times B. So we end up with this equation here. We've made K the subject of. Let's pop the units in. So why do we have 3 moles per dm3 on the bottom? Well, it's because A is squared. So there are 2 lots of them. So therefore we also have 2 lots of units. But there's only 1 of B, so we've only got 1 lot of units for B. So we're going to cancel the common units again, but this time we can only cancel 1 of the mole per dm3s on the bottom. So we're left with seconds to the -1 on the top and 2 lots of mole per dm3 on the bottom. So you never see units particularly written as seconds to the -1 over mole per dm3 minus 3. So in order to clear this up a little bit, we need to bring all of this up onto the top. And you do this in order to get rid of the divide, if you like. You've got to times everything. You've got to make the positives negative and the negatives positive. That's what I always think. So if you imagine that moles is +1 currently, and then dm's -3 minus 3. So what you do to bring it up onto the top, we end up with mole to the -1, mole to the -1. And we add our powers, so it ends up as mole to the -2. And then because we're turning on negatives into positives, we then end up with dm to the 3, dm to 3, which equals dm6. And then you want to put your units in order of highest to lowest indices. So dm6 will go first, then -1, then -2. Hopefully that made a bit of sense. So now I want you guys to have a go. Can you calculate the units for the rate constant in the rate equation above? And then I'll put a poll up once you figure that out. And if you just select the right answer. Brilliant. You're doing really well, guys. Well done. Okay, so we've all got the right answer here. I'll just go through it quickly in steps. So the first thing we want to do is rearrange. There we go. First thing we want to do is rearrange to make K the subject. So we end up with rate, it's not drawing, rate over A squared B. Those are concentrations. Then we substitute the moles into that. I think I actually have I don't have a thing showing me the results. Yeah, then we substitute the moles into that. So we end up with moles dm -3, seconds to the -1 on the top. And then we end up, oh dear, that wasn't supposed to go through that there, but anyway. Then we end up with mole to the dm -3, but we've got 3 of those on the bottom because we've got 2 lots of A and 1 lot of B. We know that one lot of it cancels. So we end up with the scenario we had before, where moles is to the -2 and dm is to the 6 in seconds to the -1. It's brilliant. Well done, guys. Good work. Okay, so we are in fact able to, so that was all sort of how we go about doing things. But when we're actually looking at experimental data, we're able to obtain the orders. Oh. And we do this by monitoring how the quantities change over time. So there are lots of different methods we can use, which I think I talk about later. There are lots of different methods we can use in order to determine the rate of the reaction. You can measure the amount of products that's being given off. For example, we could catch the CO2 given off by our calcium carbonate chips and acid. You could catch that CO2 in equipment called a gas syringe. Or you can measure the weight of it and see how the weight changes over a period of time using a balance. That's supposed to be a balance. And that allows us to figure out how much product is being made and how fast the reaction rate is. So we want to know what the initial rate of reaction is. For this one, the initial rate is the rate right at the beginning of the reaction when time equals 0. Obviously, in practice, it's very difficult to know what the rate is at t equals 0. So here we have an experiment. We've got nitrogen dioxide gas reacting with some ozone. And it's forming N2O5 and oxygen. So here we're measuring the amount of reactant, the concentration of reactant that is being put in. Okay. And we have the initial rate written down here. So if we have a look at these experimental results, we start in experiment 1, got 1 times 10 to the -3 of nitrogen dioxide and 2.5 times 10 to the -3 of ozone. And that gives us an initial rate of 3.2 times 10 to the -8. In reaction 2, we've changed something. We've kept the ozone the same, but we've in fact doubled the amount of NO2. Okay, and we can look what this has done to the rate. So what has this done to the rate? It has doubled. 3.2 times 10 to the -8 times 2 is 6.4 times 10 to the -8. So both of these have been multiplied by 2. Can you guys pop in the chat what order is the nitrogen dioxide? What order of reactant is it? Can you guys tell me? If when the concentration is doubling, the rate also doubles, what order is the reactant? Yeah, brilliant. First order. Perfect. Okay. Okay. It's first order with respect to NO2. Perfect. So what about the ozone? So in experiment 3, we're keeping the nitrogen dioxide the same as it was in experiment 2, but this time we've doubled the ozone. So, and look what effect this has on the rate. Can you guys pop in the chat what order reactant the ozone is? Okay, so not quite. So everyone's saying second. Well, let's have a think about it again. If we put these numbers, it's confusing because it's standard order. So, standard form, sorry. we're doubling the reactant. 6.4 times 10 to the minus 8 multiplied by 2 is 1.28 times 10 to the minus 7. It's confusing because of this standard form, but don't let it trick you out. So this one is in fact also first order. So can you guys pop in the chat, if both of these are first order, what is the overall rate? The overall order, sorry, of this reaction. Yeah. 2. That's really good. So the overall order is a sum of the individual orders, which is 1 plus 1, which equals 2. I think you guys are getting the hang of this, which is good. So now that we know the orders, we can now write down the rate equation. So using this template that we saw previously, oh dear, but this time, instead of there being A here, this is going to be our NO2. And instead of it saying B, this is going to be O3. So we are now able to write our rate equation, and because we know the orders. So we know that nitrogen dioxide is first order. So there's an imaginary 1 there. And we know that ozone is first order, so there's an imaginary 1 there. So our rate equation for this reaction looks a bit like this. So now we know what the rate equation is, we're now able to calculate the constant K. Yeah, we can do more questions with standard form. I'm not sure whether there are any. There might be a few coming up. We've got a few exam questions coming up in a moment, which I think have some standard form in. So we'll do that in a minute. So now we know the rate equation, we can calculate the rate constant. Do we need to write states when making the rate equation? We'll come on to that a little bit later. I know it says states, there are states here. You don't typically put the states in when you write the rate equation actually, but we'll come on to why that is in the next lesson actually. So you're ahead of yourself there. Okay, so now that we know the rate equation, we can calculate the constant K. So let's start with the units first. Make K the subject. Substitute the units in, which I know you guys are already good at. Cancel the common units. So for this equation, our units are dm3 moles to the minus 1, seconds to the minus 1. Okay, those are our units. Now we know what our units are, we're able to calculate K. And it's just a simple way. All you do is you plug the values in that you've got in the table and plug them into the equation. So what we're going to do is we're just going to use the values. I think, which ones have they chosen here? The values from experiment 1. So our initial rate was 3.2. We plug that in for the rate. And then we have NO2 and O3, and we just simply plug these numbers in. And we get K as a value of 1.28 times 10 to the minus 2. And we put the units on the end. It's as simple as that. So now we've just got a few exam questions. I'm aware that it is coming up to 10:45. So we've just got a few exam questions that we can go over now. Pop in the chat whether you want to go over these exam questions now or whether you'd like a break first. And then we can do the exam questions after the break, because I'm aware that it is 10:45 now. Break first and then do the exam questions. Okay, yep, that's fine. So there we go. So if I'll see you guys at 11, where we'll go over those exam questions and then we'll look a bit more at some graphs. So thank you very much. I'll see you at 11. Okay, so it's 11 o'clock, so I'll make a start again. Right, so we'll just go back to those exam questions and we'll have a little go at them. Hopefully you guys are feeling a bit more refreshed now and ready to do some. So this first question, the following table shows the results of 3 experiments carried out at the same temperature to investigate the rate of reaction between compounds P and Q. Use the data in the table to deduce the order with respect to P and the order with respect to Q. Okay, so if you guys could, once you've worked out the answer, pop in the chat, P equals whatever and Q equals whatever. Yep, I can give you a little bit of a clue to help you start. Okay, so let's have a look at experiment number 1. So first of all, we're changing, oh dear, I showed you the answers then. First of all, we're changing P. So between experiment 1 and experiment 2, you can see that P has halved. So now you need to have a look at the rate. What has happened to the rate? What changes there in the rate from experiment 1 to experiment 2 with respect to P? That's my clue. And then to work out Q, you can see that between experiment 2 and experiment 3, we have doubled the concentration of Q. So what has happened to the rate between experiment 1 and experiment 2? So these are a little bit more tricky because we're using standard form. So you might need to get your calculator out to try and work it out. That's what I'm about to do. So if you're a little bit stuck, what I would do is, okay, so yes, we've got some answers coming in, that's good. If you're a little bit stuck, what I would do is if you divide, so in order to figure out what the rate is, divide this number, or divide this number by this number, and it'll give you the change if you see what I mean. And the same with this one. If you 3.8 times 10 to the minus 3 divided by 1.9 times 10 to the minus 3 should give you the order. Okay, so got some good answers coming in. One person has said P equals 2 and Q equals 1. Then we have another person has said order 4 with respect to P and order 1. Okay, so we'll have a look at the answers. So P is in fact 2 and Q is 1. So well done to you guys who are getting those answers right. So P is a little bit of a trick one because we've been used to the concentration doubling or increasing, but this time it's divided by 2, so it's halved. So what's happened here? The concentration is halved, but then if we do 1.9 times 10 to the minus 3 and we divide it by 7.6 times 10 to the minus 3, we get 0.25, we get a quarter. Oh, 5. So we see that as the concentration of P has divided by 2, the initial rate has divided by 4. So that is a second order reaction. because it's just like the other way around. If this had multiplied by 2, this would then multiply by 4, and 2 to the power 2 equals 4. So this has got to be a second order reaction. And then Q is just as before, the concentration doubles and the rate doubles. So we'll have a go at this next one. In a reaction between R and S, the order of reaction with respect to R is 1. The order of reaction with respect to S is 2. And the rate constant at temperature T1 has a value of 4.2 times 10 to the minus 4. So we weren't sure about P. I'll go back to P. Okay, I'll explain P again. So the order with respect to P. So what have we done here? The concentration of P is divided by 2. We've halved it. The initial rate has been quartered. Okay. So we've divided it by 4. So this must be a second order reaction. If you think of it, let's pretend we're not halving and we're not quartering. Instead, let's times this one by 2. What would happen to the rate then? Well, we'd multiply it by 4 if it's a second order reaction, because it would be 2 to the power of 2. 4, the rate would multiply by 2. However, with this, we're not multiplying, we're halving. So a half squared equals 1 over 4. So it's still second order, but we're in fact quartering it instead of quadrupling it, essentially. Okay, cool. It's good. I'm glad I could clarify that for you. Let's move on to the next question. Okay, so in this reaction, the order of reaction with respect to R is 1, and with respect to S is 2. And the rate constant has a value of 4.2 times 10 to the minus 4. So write a rate equation for the reaction and calculate the initial rate when the initial concentration of R is 0.16 moles DM3 and that of S is 0.84 moles DM3. So you guys can, I don't know how easy, it won't be very easy to write. You can have a go at writing a rate equation in the chat if you like. I'm not sure how easy it is to type one, but I'll work through this one with you. So we have our two reactants, R and S. Oh dear. We have our two reactants, which are R and S. The order of reaction with respect to R is 1. So we know that that's a first order reactant. The order of reaction with respect to S is 2. So we know that that's going to be a second order reactant. And that the rate constant is this here. So in order to write a rate equation, we always stick to this format. So rate, I've got any answers in the chat? No. Rate equals K, which is our constant, multiply, oh, that's deleted everything. Rate equals R, sorry, we need a K there first, our rate constant K. Then we have R, which is first order to the power 1. But we remember we don't actually put the power 1. If there's no power, we assume it's to the power 1 anyway. So we don't put that. And then S is the power 2. So we put in brackets again, S, which is to the power 2. And then for the calculation, all you do is you plug the numbers into the equation that they've given you. You're plugging these numbers in. Do we lose marks if you put 1? I don't think you would lose marks if you put the 1 there. I think the examiner would have to be pretty harsh. But I suppose it's just convention to just not write the 1 there. Okay, so the answer to this one, and save you're putting in your calculators. The answer to this is 4.7 times 10 to the minus 5. And I don't think there's a mark for units on this one. I think that's what that means. But usually there will be a mark for units. And then another question. So this is our final exam question. I want you guys to have a go at working this one out for me. And just pop your answer in the chat. Hopefully you've all got your calculators ready because you'll need your calculators. So in a second experiment performed at a different temperature, the initial rate of reaction, so our rate is 8.1 times 10 to the minus 5. When the initial concentration of R is 0.7 and that of S is 0.98. Calculate the value of the rate constant at temperature T2. I'll give you a hint to get you started. Your first step is that you want to work out a rate equation. Oh, actually, which we've already worked out in the previous one. I'll just copy that down for you. That was rate K. And what power were we talking? It was R was first order, and then S was second order. So there's your rate equation. So our second step, once we've got the rate equation, we want to find the rate constant. So we need to rearrange this equation to make K the subject. So that's our second step. I'll write that there, rearrange. If you guys could all do that. And then our third step is to put the values in that they've given us. So rate 8.1 and then these concentrations. Not forgetting that we have this order here, so one of them does need to be squared. Once you guys have got your answer, pop it in the chat. It will be in standard form, I think, this answer as well. Yep, we've got one correct answer in the chat. Any more? Anyone else? Yep, brilliant. Well done, you've all got it. So the answer is 1.1 times 10 to the minus 4. Perfect. Okay, so now we've done those, we'll move on a little bit. So I'm now going to move on to talk about graphs. This part of the session should last until 12 o'clock. Okay, so concentration time graphs. So when we've been doing our rate equations, when we've been doing our experiments, sorry, we've been measuring the volume of gas produced by our marble chips, or calcium carbonate chips, sorry, the volume of CO2 given off. And we can work out the concentration. If we know the volume and we know the moles, we can work out the concentration because we know moles equals volume times concentration. We can work out the concentrations for them. And we can plot a graph. We can plot a concentration time graph. And this can be plotted from continuous measurements taken during the course of a reaction. And this is called continuous monitoring. So you're continuously monitoring the course of a reaction, how it progresses. So in a practical sense, so what you do in the lab, I have already mentioned a few already. Can anyone think of some examples of continuous monitoring? how would you continuously monitor a reaction? Can you pop in the chat some ideas of how you would continuously monitor a reaction? Like, for example, our calcium carbonate and marble chips. Yeah, so we've got an answer of number of bubbles or gases. So I wouldn't potentially do it in number of bubbles, but you're on the right track. It's you would measure the gas, but we use something special for that. Yeah, so you measure its volume. So what we can do, volume of CO2, brilliant. So what we can do is we can attach a thing called a gas syringe to this experiment. I don't know how to draw one, but a gas syringe looks a bit like this. It looks like a normal syringe. And it's attached to the conical flask. So any gas that's produced in this reaction will go into this gas syringe and it pushes the plunger out. And then this has got numbers on it, so you can measure the volume of gas being produced. So that's quite clever. And that's a good way of doing things. There are also other methods as well. I think I've got a slide on gas syringe. Yeah, here we have. So this is another one. So we have the gas monitoring. We can also measure the decreasing mass of a reaction mixture. So if we have, here they have marble chips and hydrochloric acid. So you've got your marble chips and hydrochloric acid reacting. You're producing hydrogen gas, I think, in this one. So therefore, because you're producing something, the mass of your reacting mixture is going to go down. So if you put it on scales, you're able to measure, you're able to see how much it's going down. Right. You can measure the decreasing mass and you can write those numbers down. And this is what I was talking about, the gas syringe, got your reaction mixture, and you can plot volume of gas produced over time. Yeah, you can collecting the gas and then measuring the given volume at different intervals. And then finally, something that I think is quite clever is light intensity. So if you're doing a reaction that shows a color change, you can measure the light intensity of the reaction. So here we have our light source that gets shined through the colored solution, and depending on how much light is absorbed and or reflected, that gives you a value for absorbance. So you're able to see, say for example, we have a solution and it goes from being colorless to being, I don't know, a brown color or something like that. We would then be able to measure the rate of reaction by measuring the speed of the color change. And you can use different kinds of filters within your colorimeter thing. I'm not entirely sure how it works, but you use a different filter depending on what color of reactant you've got. Okay, so now back to concentration time graphs. So if we're doing an experiment and we're collecting data, like we said, in say a gas syringe, or we're measuring the weight of something, we can plot a concentration time graph. So the concentration time graph looks a bit like this, with concentration on your y-axis and time on your x. So say at time 0, we have, I don't know, for ease, let's say that's 10. We have 10 moles of solution. That's where we are. But then at time at 10 seconds, we then work out that we've got 8 moles of solution, and so on and so forth. And we'd end up with a graph, oh dear, that looks a bit like that. That's supposed to be a straight line. And from this, we know that the gradient of a concentration time graph is the rate of reaction. And how do we know that? So we work out the gradient by doing the change in y, which is the change in concentration, over the change in x. And we've already said that rate equals concentration over time. Therefore, On this graph, we're dividing concentration by time to find out what the gradient is, and we get the rate. So the gradient of a concentration time graph is a rate. These graphs are also really useful because we can determine the order of the reactant from the shape of the graph. Okay, so a zero order reaction is going to produce a straight line with a negative gradient. Why is this? On a straight line, the gradient of this is constant all the way down, yeah? Do you agree with me? Wherever I measure the gradient on this line, it will always be the same. Say it's 10. So what does that mean? It means that as concentration is decreasing, because we're going down on the y-axis, the rate stays the same, because the rate is whatever the gradient is. So if our gradient is 10, however much the concentration is going down, the gradient will always be 10. So therefore, the gradient of the graph, therefore a zero order reactant will produce a straight line with a constant gradient. Then this gradient is going to be equal to the rate constant K. This is because if we look at our rate equation, rate equals K times by R. Say we've got reactant A this time, but this is zero order. So we don't include that in the rate equation, so we get rid of that. Therefore, rate equals K. And our rate is our gradient. So the gradient is going to be equal to constant K. Quite clever. Hey, we've been given a different graph for zero order. Do you want me to send the picture by email? So by different graph, have you got a, have you been shown a rate concentration graph? Because we're going to go over those in a moment. Yeah, so the horizontal line on the graph, that's a rate concentration graph. You've got to be really careful with the difference between them. This graph looks at concentration against time. You could be asked about both of them in the exam. And we also have another lot of graphs, and they're rate concentration graphs. Don't get confused between them. We're going to go through both of them. It's really important that before answering any exam questions, you look on the axes of your graph and you have to see what they are. Yeah, a rate concentration graph will give you a horizontal line, but a concentration time graph will give you a straight line for zero order. I hope that clears up your question. Yeah, there we go, that's what I just said. So for first order reactants, we're going to have a curved line, like so. We can't figure out the gradient of a curved line very easily anyway. This is because as the concentration is decreasing, the rate of reaction is slowing down. So our gradient is becoming shallower as time goes on. And we can see that from these little triangles that I've been drawing on the graph. So, so this is what a concentration time graph looks like. Concentration time for a first order reactant. The gradient decreases with time as the reaction is slowing down. In a first order graph, the time for the concentration to halve of the reactant to halve is constant. That's because we know that when the concentration doubles, the rate doubles, or when the concentration halves, the rate will halve. So we call this a half-life. The time that it's taken for the concentration to reduce by half is your half-life. Say here it takes 100 seconds. Your half-life is 100 seconds. So the definition of half-life is the time taken for half of a reactant to be used up. First order reactants have a constant half-life because as the concentration halves, then so does the rate. And so therefore, so does the time. The time will be the same throughout the reaction. This means you could confirm if something is a first order reaction by measuring successive half-lives. So if you look on the graph, actually I'll show you an example first. So if we look on the graph here, we're starting with 0.1, there's my thing on is there. We're starting with 0.1 moles. So what's half of 0.1? 0.05, which is here. How long does it take for the concentration of this reactant to halve? We can see from the bottom here that it takes 100 seconds. Okay, now let's look at another point. What's half of 0.05? That's 0.025, which is here. And so how long does it take the concentration of the reactant to halve again here? It's another 100 seconds. So by doing a few of these, you might get asked to do this in an exam. Half of 0.025 is 0.0125, which is equivalent to here on the graph. And again, how long has it taken to do this? 100 seconds. You might get asked to do this in an exam to figure out the half-life of a first order reactant. So here, our half-life is 100 seconds because you can see that it remains constant. As the concentration halves, the time taken remains the same. It takes 100 seconds for the concentration to halve each time. Okay. So in order to calculate a rate, the rate is what the gradient is. But as we've said, it's really difficult to calculate the gradient on a curved line. It's not simple. So we need to draw a tangent. And a tangent is just a line that runs parallel with your point as close as possible. It mirrors the slope at the point that you've chosen to figure out the rate, as you can see from here. And it enables the rate to be calculated. Yeah, so then this shows that this is a first order reaction because the half-life is constant. Okay. And the rate equation is that in this case. How would you know when to draw a tangent or a gradient? I've got another slide on tangents, which I'll move to in a moment. Okay, so what is the rate equation for this reaction? If we know that NO2, N2O5 is first order, then our rate equation is just what it says below, just first order. So there are two methods for determining K for a first order reaction that you might be asked to do in an exam. You can do it from the rate, or you can do it from the half-life. So first of all, determining it from the rate. So this is where I mean about tangents. So if you were asked to do this in an exam, you'd probably be given a graph like this. Say it was determine the rate of reaction at 0.05 moles for DM3. So you'd draw a tangent here. We know the gradient is the rate, so we'd do the change in y, which in this tangent is 0.085-ish. Well, we're using that bit, okay. So the change in y, which is 0.05 minus 0.085 over the time, which is a change in x, which is 100. And we get a rate of 3.5 times 10 to the minus 4. So that would be how you would determine the rate from a tangent. However, this is obviously quite difficult. It requires a lot of steps. You might be asked to do this in an exam, but there is a simpler way, you'll be glad to know, of how I could determine the rate of reaction. So I'll just let you take that in for a moment. Okay, So we now know that the rate is 3.5 times 10 to the minus 4 at a concentration of 0.05. So we also know what the rate equation is, and that's this bit here. So we can calculate K. So make K the subject. That's what we've done here. We've figured out the rate from the tangent, and that's 3.5 times 10 to the minus 4. We did this, we put the tangent at 0.05. So we divide it by that, and we get K of 7 times 10 to the minus 3. And then don't forget to work out the units. Got rate over that, they cancel, so we just have a unit of seconds to the minus 1. Brilliant. So now this is an extra step. This is a bit confusing, but it is easier once you get the hang of it. So we can also determine K from the half-life. So we've just determined K using a tangent. We can also determine it now using the half-life. So we've got this little equation, which is something you'll unfortunately just have to remember. But K, our rate constant, equals ln2, and that is just the, I'll show you the button on my calculator. The button is here on my calculator. That's all you need to put in for people who haven't done A-level maths. I didn't do A-level maths. So you simply plug ln2 and then t to the half is your half-life. So in that previous one, it was 100 seconds. It's also a lot more accurate, this method, because it doesn't involve drawing tangents. Obviously, the problem with drawing tangents is there's quite a big room for error if you don't draw it kind of at the right gradient, right depth. So in the previous example, t to the power half was 100 seconds. Using this information, we can now find K. So we rearrange, the equation's already arranged for us. We just plug the numbers in, plug that into your calculator, do ln2 divided by 100 equals 6.93 times 10 to the minus 3. And our units, which we've already said, were seconds to the minus 1. So you can see from this, this method that this is, in fact, a lot easier than drawing a tangent, but it does appear a little bit confusing at first. But once you've done it a few times, you'll get the hang of it. Yeah, it's much better than using a tangent. I don't know how to do it using a calculator. Okay, so all you need to do is press that ln button at the top, pop a 2 in, and put the brackets around. Like that. I don't know how well you can see it. There we go, ln2. Then we're dividing it by 100 seconds. Yep. And that equals this big number here, which is what they've got, 6.93 times 10 to the minus 3. Got it. Perfect. It just takes a little bit of practice. It's all about knowing where the buttons are and remembering the equation. Cool. So from looking at this graph, what order is the reactant in this graph? What order is it? I shall put a polyp like so. So remember that this is a concentration time graph. Oops. Remember that this is a concentration time graph. Just waiting for one more answer. Okay, so we've got a split actually. So we've got a split. Half of us think it's a first order and half think it's a second order. Okay, so we know it's not a zero order graph because a zero order graph would look like this. It would be a straight line. But this one is in fact a first order graph. Now, why is it not a second order? So I don't think they would ever really ask you to look at a second order concentration time graph in the exam, purely because it's quite confusing. A second order and a first order look virtually the same. However, a second order has a much steeper gradient because the rate of reaction is quicker, if you remember. So a second order might look more like that. And a first order will have a slightly shallower gradient, a little bit more like that. Obviously, granted, that was quite a tricky question because you wouldn't know that. But well done to those guys who got it right. It was a tricky question. So now we're moving on to rate concentration graphs. So someone put in the chat, why is it not a horizontal line for a zero order graph? Well, we're about to see why that is the case. So, rate concentration graphs. These types of graphs can be plotted from measurements of the rate of reaction at different concentrations. So, we're going to look at the different graph shapes for each order of reaction. Frustratingly enough, there's a different shape. They're different shapes to the concentration time graphs. So you've got to be careful when you're looking at them, that you don't get them muddled with the concentration time graphs. Okay, so first of all, have a look at the zero order graph. So we know in a zero order reaction that the reactant, the concentration of the reactant has no effect on the rate. So on the x-axis here, you can see that the concentration is increasing, but our rate is staying the same. Say it's 10. The rate is staying the same all the way. So as we're increasing the concentration, as we're putting more marble chips into, or calcium carbonate chips into our solution, the rate of CO2 being given off is not increasing at all. So therefore, it produces a horizontal line with no gradient. Okay. So, yeah, so A equals 1, rate equals K. For this graph, you've got to remember that K is the y-intercept. And this is what K is. Okay. The reaction rate is not changing with the increasing concentration. That's what we're saying for this one. So it's a horizontal line. Now for first order, this produces a straight line through the origin. The origin is 0, 0, this bit here. So it produces a straight line. So why is this? This is because we know that as concentration increases, as it is doing along the x-axis here, our rate increases, and that increases at the same rate. So we have the same gradient all the way up. And the graph goes through the origin because when you have when you don't have any substance, when you've got a concentration of 0 of a substance, the rate is going to be 0 as well, because, well, when you've got no reactant, you don't have a rate if it's first order. So rate is directly proportional to concentration in our first order relationship. So how would you determine the rate constant K from this graph? So I'm sure you guys, in order to know which part of the graph relates to which numbers, you relate things to y equals mx plus c. You might remember this from maths. You will have done it at GCSE, but this is the generic equation for a straight line graph. Our y in this case, what do we have on the y? We've got concentration. No, we don't. We have rate on the y, sorry. Wrong way around. We have rate on the y. So those two map up together. Then we have K. And what do we have on our x-axis? Well, we have concentration. And we know, so those two map up together. And what do we have? What is our y-intercept? Well, that's just 0. So we don't really need to think about it. And what does m stand for in the y equals mx plus c equation? That stands for the gradient. So we know from this graph that our gradient equals k. So when we calculate the gradient, that is going to be k. And that's what it says there. So how would you determine the rate constant k? You'd measure the gradient. That's a little bit complicated to get your head around, but just remember that for a first order graph, the gradient is k. So now we'll have a look at second order. It's much easier to tell the difference between a first and second order graph on a rate concentration graph compared to a concentration time graph. So as you can see in this graph, it doesn't go up linearly like our first order graph does. It goes up exponentially because as the concentration is increasing, the rate is increasing squared to the concentration. So we have an upward curve with an increasing gradient. So the gradient starts off shallower, and then we're getting steeper and steeper as the line keeps on going up. So rate, this is our rate equation for our second order reactant. Rate equals k, a to the power 2. So as this is a curve, the rate cannot be obtained directly from this graph. We don't go that far in A-level chemistry. I know you probably could do if you're doing A-level maths, but we don't quite go that far. All you need to know is this is what a second order graph looks like. For a rate concentration graph, this is what a second order looks like. It's that exponential curve with an increasing gradient. And that's because as the concentration increases, the rate increases to the power of 2. So that's what that looks like. So now just to test, you can remember the shapes of these. In the chat, please can you tell me, first of all, what order graph is the red line? If you can just pop it in the chat, what order graph is the red line? Yep, 0 order. What order graph is the blue line? Yep, first order. And that leaves, what order graph is the green line? Second order. Brilliant. So now we know. Okay. So dinitrogen pentoxide, or N2O5, decomposes to form nitrogen dioxide and oxygen. Determine the order and the rate equation of this graph. Okay. Oops. So how are we going to do this first? We need to think about it in steps. So here we have this graph. Let's think about it in steps. So from the shape of this graph, what order reactant do you think it looks like? Pop in the chat. From the shape of this graph, what order reaction is this? Yeah, first order. So that's our first port of call. So we can see that N2O5 is a first order reactant. Okay. So how would we write that as a rate equation? Yep, so this is what it says here. This graph is a straight line through the origin, first order with respect to N2O5. So our rate equation for a first order reactant, rate equals K, our constant, times by N2O5, and that's first order. It's to the power 1, but we don't write 1. Now, we want to be able to determine the rate constant K. So, first of all, step number 1 here. In order to determine the rate constant K, we need to rearrange our, so I always try and rearrange the equation first. So K equals N2O5 over, oh no, sorry, K equals rate over N2O5. So, and then I also note, hang on a second, this is a first order graph. Rate divided by N2O5 is also the gradient. That's the change in Y over the change in X. So what we need to do, we know that K in a first order reaction is equal to the gradient of the graph. So the change in Y for this one here is 0.003 and the change in X is 0.6. So to work out the gradient, we need to calculate it. So divide those two and we have a rate constant of 6.4 times 10 to the minus 3. And remember those units. For this equation, they're seconds to the minus 1 because it's first order. So we can also do it via the initial rate method. The initial rate is the instantaneous rate at the start of a reaction when T equals 0. The initial rate can be found by measuring the gradient of a tangent drawn at T equals 0 on a concentration time graph. Remember that rate equals concentration divided by time. Therefore, the initial rate can only be found by drawing a tangent on a concentration time graph, because when we calculate the gradient of that tangent, it will be concentration divided by time, which equals rate, if you understand what I mean. So you can imagine that this is really difficult in practice to work out. It's really hard to measure the rate instantaneously when it goes in, when your reactants go together. So for example, keep going back to this reaction, but it is quite a key one. Calcium carbonate and your hydrochloric acid. So there's going to be a gap in time, because once you put the calcium carbonate chips in, you then need to attach your gas syringe onto the equipment. There's going to be a gap in time kind of as you do that. So you're never going to be able to measure the rate instantly at T equals 0. There are a lot of kind of practical implications behind this. And also the same, it might be a little bit easier if you're measuring the weight of it. So if you've got your conical flask on here, you pour your marble chips in, or your calcium carbonate chips into your flask here, and you measure the weight instantaneously. It is just very difficult in practice. So there are these things called clock reactions. A clock reaction, you might have seen an iodine clock reaction, but it's a way you can obtain the initial rate by taking one single measurement. So the time T from the start of an experiment is measured for a visual change to be observed. Often that's the formation of a colour or a precipitate. A common reaction that we use is called A common reaction that we use is called the iodine clock reaction. The iodine clock reaction is a really good one to use for this because initially the solution is colorless and then it makes this, and then it becomes a kind of a black color, I think. So the way this kind of maths works behind this, I find this quite difficult to get my head around. Why is the initial rate the same as like the time it takes for a color change to take place? Like, why is it so? So we're assuming there's no significant change in rate during the time. It can be assumed that the average rate of reaction over the time it takes for the reactant to change color is the same as the initial rate. Initial rate, we then say, is proportional to 1/T. And the clock reaction is then repeated with lots of different concentrations. And the values of 1/T are calculated for each experimental run. Okay, so it doesn't start colorless, sorry. It starts as an orange-brown color. Iodine, you might have seen in the lab. It is initially an orangey brown color. And then your timing, I've got your stopwatch here. Bit of a rubbish stopwatch, but got your stopwatch here. Your timing, you're watching for a color change. And it's going to go from orange brown to dark blue black. And you're measuring this time with your stopwatch. And you change the concentration and you see how long it takes. That's what happens with an iodine clock reaction. So why does it take so long to change color? It's because there are lots of other reactions going on within our reaction mixture before it gets to turning it dark blue and black. And all of those reactants and products have to be used up before it moves on to the stage where it turns dark blue black color. Basically is what happens. And that's what an iodine clock reaction is. So yeah. It's now kind of just about lunchtime. If anyone has any questions, I know we finished like 5 minutes early this time. If anyone has any questions or wants me to clarify anything, I can do. I can go over them for the next 5 minutes, or you guys can just have a lunch break now. And yeah, what do you want to do? What exactly do we need to know about the iodine experiment? I'm not entirely sure. I've not looked at the specification. The Ask Ace might know better than I do. What exactly they need to know about the iodine experiment. Please can you go over clock reactions again? Okay. Yep. Yeah, so we'll just go over clock reactions again. Clock reactions are very confusing and I struggle to understand them too. Okay, so a clock reaction is a way of obtaining the initial rate of reaction by taking a single measurement. Okay. So we replace this because, as I said, it would be really impractical to try and measure the rate of reaction with something that's going really fast. Whereas when you can just see a visual change, something changes color, that's much easier to measure the rate of reaction from. So the time is measured from the start of an experiment until a visual change takes place. In the context of our iodine clock, it's the time it takes from the start of the reaction till that dark blue precipitate is formed. Okay, so provided there's no significant change in rate over that time, so we're presuming that this reaction is taking place at the same rate. So the average rate of reaction of those first, I don't know, say it takes 10 seconds for it to turn dark blue. We're presuming that's the average rate of reaction over that time. We then say that the initial rate is proportional to 1 over t. 1 over that time that we've just measured, so 1 over 10. And then this reaction is repeated lots of different times at different concentrations. So you're putting different concentrations of iodine in there, different concentrations of starch, different concentrations of things. And the values of 1 over t are calculated for each experimental run. And we then use these values to calculate the initial rate. I don't think you need to know how to do it. It's not been included on my PowerPoint slide, so I presume you don't need to know exactly how to calculate the initial rate, but just know that this is a way we can do. So, as I mentioned, the iodine clock relies on the formation. When iodine reacts with starch, it forms this dark blue-black colour. So you measure the time it takes for it to form a dark blue-black colour. At the start, lots of other reactions are happening, so there is no colour change. But then suddenly it will react with the starch and we'll get this dark blue-black colour forming in our iodine clock. We can do this lots of different times at different concentrations and work out our initial rate from this. I hope that clarifies things. It is confusing, but I wouldn't worry about it too much. So, right, so I'll see you guys. It's now time for lunch. And we've got a half an hour break this time. So I'll see you guys back at 12:30, where we'll be looking at temperature and its effect on rate of reaction. So it's 12:30, so I'll make a start again. I hope everyone had a nice lunch break. This session is going to last until about 1:10 when we'll have a break. Okay. So we're now going to talk a little bit about multi-step reactions. So you will have seen previously that our reaction, an overall chemical reaction, compares the reactants and the products. Okay, the balancing numbers give the stoichiometry, which is just the numbers before things, and the relative amounts of each species in the reaction. So, for example, we have this reaction here. I think that's hydrogen peroxide reacting with iodide ions and hydrogen ions to form iodine and water. So this is a full equation which we're used to seeing written down. However, in real life, do you think that this reaction is going to occur all in one step? Well, the answer is no. It's very unlikely that this would all happen all together in one step. Because as it says here, for the reaction to take place in one single step, a molecule of H2O2, 2 iodide ions and 2 hydrogen ions have to all collide together simultaneously. And obviously that's a very unlikely event. It's much more likely that 2 ions are going to collide together as opposed to 4 ions and a molecule of H2O2. So such reactions are more likely to take place in a series of steps. Because it is just so unlikely that more than 2 particles are going to collide at the same time. Although we write it out like this just for ease to show what the overall reaction is, what the overall reactants are and overall products are of a reaction. So the series of steps that make up your overall reaction are called the reaction mechanism. And that is how it works. Within a multi-step reaction, if you've got, say, 3 different steps, 2 or 3 different steps in your reaction, those are going to take place at different rates. They don't all happen at the same speed. The slowest step in this sequence is called the rate determining step. Okay. I've got a really good way of explaining this and how it works. So imagine you're baking a cake. In order to bake a cake, you don't simply put all of the ingredients in the bowl together and then you have a fully baked, fully iced cake. It just simply doesn't work like that. You have to do it in a series of steps. So step 1 is weighing out your ingredients. Step 2 would be mixing them all together. Step 3 is baking and cooling the cake. And then step 4 would be icing your cake. Now, what does this have to do with chemistry, you might ask? So here we have 4 steps in our reaction mechanism of baking a cake: ingredients, mixing, baking, cooling, and icing. These steps all take varying amounts of time. Anyone that's ever baked a cake before knows that some steps are faster and some steps are slower. When you're baking a cake, often the baking and cooling section is the longest. So we would say that this is our rate determining step. That one is our rate determining step. This is because the baking and cooling must always happen at the same time. Imagine your cake takes an hour to bake in the oven. You can't change that time. You can't make that faster or slower. You can't bake it for half the time because you'll have a raw cake. You can't, if you bake it for double the time, you'll have a burnt cake. So this time is constant. And you know you're going to need a couple of hours to cool it. So this is the rate determining step. This is a step within a reaction that determines how long it's going to take for it to take place. The baking and cooling step. You can speed up weighing out the ingredients and mixing the ingredients together, but it won't make much of a difference on the overall speed of the reaction. Okay, so back to chemistry and not cakes. So chemists like to know what these different steps are in a reaction. And they like to propose possible mechanisms for these reactions. So, but how do they know how the reaction is going to proceed? So, our rate equation only includes the reacting species involved in the rate determining step. Okay, what does that mean? We learned before that any reactants that are zero order, i.e. have no effect on the rate, aren't included in the rate equation. Therefore, they're not in the rate equation, so it won't be determined in the rate determining step. And then the orders in the equation match the number of species involved in the rate determining step. So I've got an example on the next step. Next page. So a tertiary haloalkane is hydrolyzed by aqueous alkali, like so. This is your overall reaction. These are your reactants and your products after this reaction has taken place. So the rate equation, they figured it out experimentally, and they found that the only reactant that has an effect on the rate is this first one here. This is what our rate equation is. But we now know that the OH minus ions, our other reactant, don't have an effect on the rate. So they're a zero order reactant, or they just don't have an effect. So this means that the slow rate determining step must only involve one molecule of this compound. That's because we know that the order of this is to the power of 1, because there's nothing else written there, so it's got to be to the power of 1. And the OH minus doesn't have an effect because it's not in the rate equation. And so it must be involved in a fast step. It must be involved in a different step. Okay. So how do we work out what our rate determining steps are? So we know that the slow rate determining step only involves one molecule. The OH minus has no effect. So we can write it out. So write yourself a template. This is what I'd recommend. If we're saying you'll only get reaction mechanisms taking place in 2 steps, I think, for your exam. So you won't ever have to think about 3 or more. But imagine, so this is your rate determining step. It involves one of these molecules. And then this is a second step with the OH minus, because we know that these two aren't involved in the same step. We know what our overall equation is. That's down at the bottom here. That's our overall equation. So obviously there are some things we've not accounted for the products here at all. One question. I'm confused, I don't get it. Okay. So I'll go back over it again a little bit. So reactions have got to take place in steps because everything can't react all at the same time all together. This carbon compound here, this haloalkane here cannot react and do everything it needs to do all in one step. Okay, it's got to happen in more than one step. And what we're trying to do is we're trying to figure out what those 2 steps are. And those 2 steps, like with our cake analogy, have go at different rates. We have a slow step, which is our rate determining step, and a fast step, which doesn't have any effect on the rate. Okay? So rate equals K, and then our haloalkane. Okay. We know that because this is the only product, the only reactant, sorry, that affects the rate, that this must be part of the slow step. And our slow step here is step 1. Then we have this other reactant, which is we can see here in the overall equation. That's not involved in our slow step because it's not in the rate equation. So that's got to be involved in step 2. Yeah. I hope that explained it a little bit more. It is quite a confusing concept to understand. Hopefully you'll get it a little bit more as we keep going along. So now we're going to try and work out what these 2 steps are. Okay, so now we've got to find an intermediate molecule. What do I mean by an intermediate molecule? An intermediate molecule is something that's made in between, at the end of, like, say, this step here, at the end of step 1, but it's not included in the overall reaction because it gets used up. So an intermediate is made. So we know that this first one, that this haloalkane is reacting. And we know that we have a product bromine. So we know that this bromine has got to come off somewhere and must go on to form another product. So we know that bromine is going to be a product in step 1. When you remove bromine, which is a negative ion, an anion, from here, you are left with trying to draw it, plus a positive charge and then a bromine. Okay, that's what you're left with. However, as it says down here, this compound here doesn't appear in our overall equation up here. So it must be used up in the next step, which means that it must be one of the things that reacts in step 2. Okay. So, yep, as we've just said, we know that this is now going to be a product and this is going to be a product. But because this isn't involved in the overall reaction, this has got to then be used up. So we use it up as a reactant in step number 2. It combines with our OH- ions, which we've already worked out are there, and it makes our product. So let's see how it all works. So if we add it all up, so we have this reactant here, we have in step 1. OH- ions, we have in step 2. Those are our 2 reactants. We then produce this, which we found in step 2, and a bromide ion, which we've made in step 1. And then because this positive ion gets used up, it cancels each other out, so it's not involved in the overall equation. So we found our reaction mechanism. So can you guys think of a factor that might increase the speed of this reaction? If you pop in the chat. Yeah, I think increasing the concentration would do. I'm thinking of something quite specific, I think. Is there anything else? Temperature. Yeah, that was the one that I was looking for. Perfect. Yeah, catalyst would also increase the speed of the reaction too. But yeah, temperature was what I was looking for. So, so now we know that reactions happen in a series of steps. We're going to look at the effect of temperature on rate constants. So, as the temperature increases, the rate of reaction also increases. The rate constant K is also going to increase. Temperature is one of the only things that increases the rate constant. Okay, so I'm going to go back to my cake analogy again. If we had those 4 steps, if you remember them, if we increase the temperature at which the cake is baking at, then it will take a shorter amount of time to bake the cake. So this is pretty much what happens in chemical reactions. If you increase the temperature, the reaction is going to happen quicker because we've altered the rate determining step, if you see what I mean. And the rate determining step in our cake was baking and cooling. So how does temperature affect the rate constant? I don't know if you guys have ever seen this graph before, but I think you'll probably go over it in more detail in another lesson. But this is a Boltzmann distribution. So this is a Boltzmann distribution. On our y-axis, we've got the number of molecules. And on our x-axis, we have energy. So in any given substance, say I've got a box here, and I've got lots of particles in my box. They're not all moving at the same speed. They're not all moving, say, they're not all moving at 10 miles an hour, say. Some of them are going to be moving at 1 mile an hour, and some of them might be moving at 20. The Boltzmann distribution shows the average amount of energy, well, shows the distribution of particles at any given energy. So for example, the particles here might have energy of 1 joule, whereas the particles up here, there might be, say, 20 particles up here with energy of 10 joules, and there might, say, be 5 particles here, or no, maybe, yeah, 5 particles here with energy of 20 joules. So what a Boltzmann distribution shows you is a distribution of all the particles within a substance, how much energy those particles have. And we can see from this curve that the majority of the particles here have 10 joules of energy. Some of them have less, and some of them have more. Okay, but fewer are at higher energies, and most of them stick around 10. When we increase the temperature, what we're doing is we're giving energy to the particles in that substance, to all of those molecules. So we're giving them more energy. So what we say that our Boltzmann distribution shifts to the right because energy is increasing on the x-axis. And so more particles now have more energy. Okay. So it's shifted. So this red line represents it here. It's shifted over to the right. So what is this EA business? EA stands for activation energy. In order for particles to react, they have to have a certain amount of energy. That's the reason why that our everyday objects don't just start reacting with each other randomly. And it's why if you heat something up, it's more likely to react. So we have to have this activation energy in order for things to react. So this line is drawn here, and we can see that for the blue line, this many particles, say that represents 10 particles, have enough energy to react and are going to react with each other. When we increase the temperature, the activation energy stays the same because that's fixed. But now we have more particles with enough energy to react. And so At a higher temperature, a greater proportion of the molecules can overcome the activation energy and are able to react, because there's a bigger area here under the graph. I'll just highlight it there. It's a much bigger area under the graph. So that's what our Boltzmann distribution is telling us. So as the temperature increases, the particles move faster and collide more frequently. We know that from particle theory. To react, particles must also collide with the correct orientation. So that's just a point to note. And I think potentially could ask it in an exam. But not only do they have to have the right activation energy, they've also got to have the correct orientation. With increasing temperature, the increased frequency of collisions is comparatively, it's comparatively small compared to the increase in the proportion of molecules that exceed the activation energy. So the change in rate is mainly determined by the activation energy. So now this brings us on to the Arrhenius equation. So the Arrhenius equation takes into account temperature. Before, we presumed that all of our reactions were taking place at a constant temperature, and the only thing that was changing was the concentration. Now, we're going to think about what happens when we try to change the temperature of our reactants. Okay? So, the Arrhenius equation is quite overwhelming, but I'll break it down for you. So, we have K, which is familiar to us here. K is, of course, our rate constant. Then we have A, which is called the pre-exponential factor. You will either be given A or you'll have to work out A. Oh, don't worry about A too much. Then we have E. This little E here is another button on your calculator. So I'll show you on mine. So on mine, when you press shift, shift and then the LN button, it comes up with an E. You can see that. There you have an E to the power. So that's all that is. We call that the exponential factor, and you learn about that in A-level maths. But for this, you simply just plug it into the equation. Shift and what button? It's shift and then the LN button that we saw before. Well, it is on my calculator anyway. It could be different on yours. It's a bit difficult for you to see. Right, it's, oh, it's the other side. See the LN button, the little E's just at the top of there. So yeah, so shift and LN, and it comes up with the E for me that you can plug in. Okay. So yeah, so then we have this exponential factor. And then we have EA, which is our activation energy, which we saw earlier. R is the gas constant. So once again, don't worry about that. We know that that's always going to be 8.314. That doesn't change. And then T stands for our temperature. But just to make things a bit more confusing, your temperature is in Kelvin. I don't know whether you've ever heard of Kelvin scale. We obviously predominantly use degrees Celsius, or if you're in America, Fahrenheit. But for this equation, we use Kelvin. And to convert between Celsius and Kelvin, what you have to do is add 273. So say, for example, say today it was 10 degrees. That in Kelvin is 283 Kelvin. Just add 273 to anything in Celsius. They like to trick you out by doing that in exam questions. Just add 273. Okay. So now we've taken apart that equation. Have a look at what each bit means. This represents the proportion of molecules that exceed the activation energy and have sufficient energy for a reaction to take place. Okay? The pre-exponential factor, which you don't really need to worry about, takes into account the frequency of collisions with the correct orientation. So there's that word again, correct orientation. All we need to be able to do is to look at it on a graph and plug some numbers in. So in maths, there are these things called logs. As I say, I didn't do A-level maths, so don't worry about that. But what I learned is the opposite of E is ln, is ln, okay? So if you want to get rid of this horrible exponential thing that's going on up here, all you do is you times everything by ln, and that's what's happened here. So when you times k by ln, we get ln k. We get rid of this horrible E, and we end up with EA over RT, and then the A is also times by ln, so then we end up with ln A. And it makes the equation a bit more usable as well, because we've not got this horrible exponential factor involved. So that's all you do. Just remember that ln is the opposite of E if you're ever rearranging this equation. It also enables you to calculate EA and A to be determined graphically. Now, how does that happen? Another question. So which equation do we need to remember? If you remember this one, then you can always remember how to convert it. If you remember this one, you can always remember how to convert it into this one. I can't remember whether they give you this equation in the exam or not. I don't know whether anyone else can clarify whether they give you this equation in the exam or not. I know there are a lot of them they don't give you, but it'll depend on your exam board as well, I think. But just clarify that. So we like to plot graphs with our Arrhenius equation from our experimental data. So if you remember before, I was plotting things onto y equals mx plus c. So if we line this up with y equals mx plus c, we'll plot y. On our y-axis, we're going to plot ln k. On our x-axis, we're going to plot 1 over t. Our y-intercept is ln a. And our gradient is going to be negative activation energy over r. But remember, we know what r is because it's a constant. So, yeah, and it gives a downward straight line. And our gradient is minus EA over R. Okay, so here's an example question. Right, so we're given these values. We're given the values of temperature and our values of K. So hydrogen peroxide decomposes to form water and oxygen. The rate constant K varies with temperature as shown in the table. So we can see that as the temperature here is increasing, our rate constant K is also increasing. Oops. Plot a suitable graph and calculate the activation energy and frequency constant A for this reaction. So we've just worked out on our graph y equals mx plus c. We need to plot, what did we say? ln k on our y-axis. Yeah, where's my pen gone? There it is. ln k on our y-axis and 1 over t on our x-axis. Well, it's handy because they've given us the values that we need. We just need to change them a little bit. So the first step is to calculate the values of ln k and 1 over t, so we're able to plot them graphically. So that's what they've done here. All you've done is 1 divided by 295 equals 0.00339. That's all they've done. And they've just simply put ln brackets this number here into their calculator to get the values here for ln k. Right, so that's the first step. Now the second step is we need to plot this graph. So here we have plotted this graph, and they've found it's a straight line. It's a straight line, like this. Okay. So the next step is we need to calculate the gradient. Because if we remember, we said that our gradient is equal to EA over R. So we know it's a negative gradient. We can see that it's sloping downwards as opposed to up. We can see that it's a negative gradient. So we now need to calculate it. So for this one, it's change in y over change in x. So we're doing minus 1.90 divided by 0.0002. And we've got a gradient of minus 9,500. So we said that gradient is EA over R. Okay, we just want to work out EA. So if we rearrange it, equals G for gradient. So we know that EA has got to be our gradient times by R. From the last slide, we know that R is our gas constant. We already know what that is, which is 8.314. So in order to calculate our activation energy, we do the gradient, which is minus 9,500, multiplied by 8.314. And we come up with this number, 78,983 joules per mole. And we can put that into kilojoules, which is 1,000 times bigger. So we just end up with 79 kilojoules per mole. Hopefully that makes sense. Now, that wasn't the only thing they asked us to do. No, I don't understand this at all. Okay. It's very, I know it's very overwhelming and difficult because of all the funny equation that you get given. Okay. So what we're trying to do, I'll go back to the basics. So what we're trying to do with the Arrhenius equation is we are trying to calculate K as it changes when we do our reaction at different temperatures. So we've got our calcium carbonate chips. Okay, and we do the first reaction at 10 degrees and our second reaction at 20. Yeah. And so we can calculate the rate constant from that, like we did earlier, and also the temperature. And we can insert them into the Arrhenius equation. Where's our Arrhenius equation gone? Here it is. You can pop them into our Arrhenius equation with K for rate constant here and T for time here, for temperature there, sorry. This is a really confusing concept. So what we've done is we've plotted a graph. We wanted to know what the activation energy was. In our equation, we have our activation energy here. We want to find out what that was. So what we've done is we've plotted a graph. Those results that we got from our experiment as to what lnk was and to what our temperature was, we worked them out and we've plotted them on a graph. And we've put lnk on the y-axis and we've put 1 over t on our x-axis. Okay. We've discovered, we know that our gradient is equal to EA over R. And we wanted to find EA. So we calculated the gradient of the graph. And then we rearranged the equation to find EA. I don't know whether that makes any more sense. It is a very confusing concept to understand. So yeah. Right. So there was another part to our question. The second part was we wanted to calculate ln(A). We know from our previous, when we link this up with y equals mx plus c, we know that ln(a) on this graph has got to be our y-intercept. Okay, so on this graph here, what we've done is we've extended it back. So you continue the line. This is what you do in real life. You'd continue the line after you'd stopped until it reaches the y-axis. Okay, and so that value is equal to ln(a). ln(a) is 25.4. To work out a, remember that ln is the opposite of e. So we do e to the power of 25.4 is 1.7 times 10 to the minus 11. So that is our value for a. Okay. I think the key to this is practice. You've got to sort of go through a few of them with the steps. You'll get the PowerPoint at the end of the session. Use the steps that the PowerPoint is laid out for you and go through some practice questions trying to work out these numbers. We don't have time really today to do that. But yeah, I recommend going through them just again and again and practice. And you'll also go through it in lessons as well. So yeah. Yeah, you can email me if you're unsure or stuck. Yeah, you can email Ace Medics. I think you have their email address, don't you? Or yeah, and I'll get them to pass my email on to you. You can always email me if you're stuck and you need help with questions, but just try to apply this same format that we've used here when you're answering the questions, and practice does make perfect. The more practice you get, the better you'll get at it. So yeah. Yeah, I realized that was a very intense session. So thank you very much. We finished like a minute or so early. But yeah, I'll see you guys back at about 1:20, I think. And we're going to just talk a little bit about equilibrium briefly. Okay. Okay, so I'll see you then. Okay, so it's 1:20 now, and we're just going to start again. Start for the final section. So I'm going to just talk a little bit about equilibrium. I'm only going to go into it briefly because we don't have that much time, and then we'll have a little clinical skills corner just to round off the day. Okay, so we've just seen the rate constant, which was K. Well, we also have a thing called an equilibrium constant, and we call it Kc. You might be familiar with the equilibrium constant already from previous chapters. I'm not sure kind of what bit you've done. But we have this thing called dynamic equilibrium. So dynamic equilibrium exists when the rate of the forward reaction is equal to the rate of the reverse reaction. And what chemists like to do is to calculate the position of equilibrium. So we have this equation here. Say that more products are being made than reactants. We're going to say that the equilibrium is somewhere over here, where this dot is. Okay. However, if, say, more reactants were being made than products, then we would say the equilibrium is somewhere over here. But if exactly the same amounts were being made, the equilibrium would be in the middle. So we are able to calculate where the position of this equilibrium is from the amounts of products and reactants being made. So can you write the equation for the equilibrium constant for the following reversible reaction? So I'll show you first on a practice question. So here's our reaction. So A plus B makes C plus D. And in order to work out the equilibrium constant, we do concentration of products over our reactants, and that's what Kc equals. So if we plug these numbers in, we get this. With our orders, the power was the order of the reaction. For this, the balancing numbers in our equation, which are represented by the lowercase letters here, those are the powers. So C, there are little c amounts of big C. So C is to the power C here. It will make more sense when we put real chemicals in. So then we also have the square brackets. You saw them when we were in our doing our rate equations. Well, square brackets are shorthand for concentration of. So if you ever see square brackets, we know that it means concentration of products over concentration of reactants. So that's how we work out our equilibrium constant. Yep, and then A, B, C, and D are the balancing numbers. And those are the concentrations of the reactants when it is at equilibrium. So when the rate of the forward reaction is equal to the rate of the backwards reaction. So can you write Kc for the following reaction? You can have a go at writing it in the chat. If you just use a slash as like the kind of the over something else sign, so just write it. Oops. You can have a go at writing it in the chat. Always remember it's going to be products over our reactants. Yep, we've got some answers coming through now. Yep. Brilliant. Well done, guys. Got them all right. So, yep, that's going to be our equilibrium. reaction equation. Oops. Always remembering that the powers in this one are the balancing numbers in the equation. So we've got 2 lots of ammonia here, and so we've got it's to the power of 2. Okay, what are the units of Kc? So to work out the units, we do the same thing that we did for the units of the rate of reaction constant. So for the following reaction, this is what our this is our expression for Kc, which we're looking at. So we're measuring it once again in concentration. So we have 2 lots of hydrogen iodide on the top, and then we have 1 lot of H2 and 1 lot of I2. So in the end, there aren't actually any units because they all cancel out, because we've got 2 of these and 2 of these, they all cancel out. So in fact, Kc doesn't actually have any units in this case. Okay. Can you guys now calculate the units of Kc in each of the following reactions? If you just put your answers in the chat with 1 and what the units are, and 2 and what the units are. Yeah, so yeah, if it's to the power of 2, you do write the units twice on the top because there are 2 lots of units. Yeah, so number 1, have a look, what have I got answers to be? Yeah, we've got 1 answer in, it's nearly right, there's just 1 tiny bit I'll go through in a minute. Yeah, I'm wanting the units. So that's really good. You've written me the equilibrium constant, but what are the units? Yep, that's good. The last one, that's good. Okay. So I'll just go through the answers. Oops. Okay, so for number 1, we've got 2 lots of NO2. So that's going to be mol dm minus 3, mol dm minus 3. Let's close that down. Over, where's my mouse gone? Oh, it's there. Over 1 lot of N2O4. So yeah, you guys are right. You just cancel out those 2. So your units are just mol to the dm minus 3. For this bottom one though, it's a little bit trickier. So we have mol minus 3 on the top. And then on the bottom, we've got 3 lots. I'll just write it like that. So we know that 2 of them cancel out. So we're just left with 1 over mol dm minus 3. Now to bring it round to the top, we've got to make our negatives positive and our positives negative. But we've always got to remember there's a sneaky 1 after this mol. So we end up with mol to the minus 1 dm to the 3. And that's how they trick you out, because you always forget that this mol has a sneaky 1 after it. Okay. Right. So types of equilibria. Equilibria are divided into two main types, depending on the state of the reactants. We've got homogeneous and heterogeneous. Heterogeneous. Homogeneous equilibria, all of the species are the same state or phase. So homo means same. So you can just remember that by breaking the word down. Homo means same. So it means that all of the species involved are the same state or phase. Heterogeneous equilibria, on the other hand, hetero means different. So all of the equilibrium species have different states. So different states, so some of them are liquid, some of them are solid, some of them are gases. Whereas with homogeneous equilibrium, all of them are gases or all of them are liquids. So if we call this one number 1 and this one number 2, can you tell me whether 1 and 2 are homogeneous or heterogeneous equilibria? Just write 1 is whatever, 2 is whatever. Yep, 1 is homogeneous and 2 is heterogeneous. There we go. Brilliant. Got those right? So it's as easy as that. Okay. In homogeneous equilibria, the Kc expression contains concentrations of all species. However, in heterogeneous equilibrium, the concentrations of solids and liquids are essentially constant within the equilibrium, so we get rid of them from the Kc expression. So we only have the concentrations of gases there. So for example, with this equation, when we write the Kc equation, we don't put carbon in there, we get rid of it, and we only include the gaseous compounds. So we end up with something looking a bit like this. Yep. And those are our units. So now this is a little bit more challenging. Where have we got up to? So this is a little bit of practice. So what we're trying to do here with this equation, using this equation, work out the equilibrium amounts of all equilibrium species. So I'm just going to do this one with you guys first, and then so you can see how it works. I'll show you how I do it, and then you can practice them more in your own time. So we know that 1.6 moles of nitrogen oxide are mixed with 1.4 moles of O2. This is at the start of the reaction, so there are no products yet. So we're not in equilibrium yet. This is what they just mixed together. Those are our initial reactants. These are mixed together in a container with a volume of 4 DM3. Okay. Then at equilibrium, 1.2 moles of NO2 gas has formed. We want to calculate Kc. So this is supposed to be 2. There's supposed to be 2 there. There we go. So we put our reactants in, certain moles, and then we get 1.2 moles of NO2 when we reach equilibrium. But what we need to find out in order to calculate Kc is how many moles of nitrogen oxide and oxygen are there when we're at equilibrium. We know how much there is initially, but we don't know how much was at equilibrium. So I use the acronym ICE to help me work this out. So I stands for initial. So I'll do this underneath here so it lines up. So if I can get it to line up. So the initial amount of NO they put in was 1.6 moles. The initial amount of oxygen they started with was 1.4. And because this is the start of a reaction, there aren't any products yet. That's a 0. Okay, that's our initial amounts. Okay, oops, ignore that line. So now we want to look at the change. So our nitrogen dioxide, we know, started at 0 and has increased by 1.2. So change, but we don't know what the changes of these two yet. And then now we write a final column for our values at equilibrium, E. So we don't know what these two are, but we know that there's 1.2 moles at equilibrium. Okay. So, oh, I've got some messages popping up in the chat. Is it meant to be 2 NO2? Can you explain it again, please? Yes, I think it is meant to be 2 NO2 because that balances up, because we've got 2 oxygens here, 2 oxygens here, whoops, 2 oxygens there, and then we've got 4 oxygens here. So it is supposed to be 2 NO2. Which bit do you want me to explain again? The box bit, this table thing that I'm drawing here. Yeah, okay. So this table, so I stands for initial. So this is the initial number of moles. C stands for change, the change in the number of moles, and E stands for the equilibrium amounts. Okay. From the question, we're told that our initial amounts that are mixed together are 1.6 moles of NO, which we've put here, and 1.4 moles of O2, which I've put in here. And because this is the start of the reaction, we've not made any product yet. So we've got 0 moles of NO2. Then, now we have the change. We want to figure out how many moles there are left at equilibrium once this is reacted. So we need to know what the change is from the initial amount to the equilibrium amount. All we know is that at equilibrium, we have 1.2 moles of our product. Yeah, because that's what it tells us in the question. So we know that it's plus 1.2. That's the change for that. We know that these concentrations here are going to go down, 1.6 and 1.4. It's going to decrease because as more product is made, there'll be less reactant. So now we need to think about the ratios. So we've got 2 moles of NO. We've got 1 mole of oxygen, and we've got 2 moles of NO2. So we have the same amount of NO2 and NO. So if the NO2 has increased by 1.2 moles, because we're the same ratio, a 1-to-1 ratio, it means that the NO is going to decrease by 1.2 moles because it's a reactant. So if we put minus 1.2 in here for this. Now, our O2. So with our O2, that is a 2-to-1 ratio. We have 2 nitrogen dioxides for every 1 lot of oxygen. So if our change is plus 1.2, our oxygen is only going to go up half as much. So our change is only going to be 0.6. And again, because it's a reactant, that's minus 0.6. Okay. So then we end up with our equilibrium amounts being 0.4, because 1.6 minus 1.2 is 0.4, and 0.8. So now we've used that equation and we've worked out the equilibrium amounts of all of the species. So now we know those numbers, we can put them all into the equation we worked out previously. I think a table will just come up, which explains it a bit better, but all my writing's over it now. Yeah. So yeah, here we are. If you can see through my scribbles, this is what they've done. And they've worked out the amount at equilibrium there at the bottom. Okay, so that was the moles, but we want the concentration. Because remember, the square brackets in our equation denote concentration. So we want to find out what the concentration is. So we've got the moles. Total volume, they told us in the question, was 4 decimeters cubed. So in order to work out our concentrations, we simply divide by the volume, because concentration is moles divided by volume. Mole over volume. So we'll divide everything by 4. Yep. So dividing it by 4, we get these amounts. So now we've converted it to concentration. Okay. Right. So now finally, what can we do? We can plug it into the equation. So got our concentrations. What's our expression? So our expression is products over reactants. So it's NO squared over, oh, NO2 again. Keep missing the little 2 off. Over NO squared O2. Yep, that's what they've got there. And then we simply just plug the numbers in. So 0.3 squared divided by 0.1 times 0.2. And we then have our expression for K. Okay. So and then the next little bit I'll just talk about briefly because we are running out of time. So that's what equilibrium is. And then we have the equilibrium constant Kp. So before we talked about Kc, well, we also have another equilibrium constant, and that's called Kp. And Kp we use for gases. So equilibrium involving gases are usually expressed in terms of Kp. The equilibrium constant in terms of partial pressures. So what is a partial pressure of a gas? For gases, it's easier to measure a pressure than it is a concentration. Concentration and pressure are proportional, and therefore Kp has a direct relationship with Kc. We can think of it as the same thing. So a mole fraction, that's what we have to work out. Under the same conditions of temperature and pressure, the same volume of different gases contains the same number of moles of gas molecules. What do I mean by that? A mole fraction of a gas is the same as it is proportion by volume to the total volume of gases in a gas mixture. So, say I have 10 moles. I've got a box, and inside that box, I have got 10 moles of gas. 5 moles of that are oxygen. I've got 2.5 moles of carbon dioxide, and I've got 2.5 moles of nitrogen gas, all within this box. But in total, we have a total of 10 moles. We can work out a mole fraction by the number of moles of A, say A is the oxygen, which is 5, divided by the total number of moles in the mixture, which is a half, 5 over 10. I don't understand what Kp is. Okay, so Kp, Kc was our equilibrium constant for the state of anything. So have I got an equation on the next slide? I need a good equation to explain what Kp is. So if you remember, this is going back to Kc. Kc was where is the position of equilibrium. So if you're making more products, the position will be over here. And if you're making more reactants, the position will be over here. Kp is simply Kc, but we use pressure instead of concentration. Okay, so if we have I think that's balanced. No, that's really not balanced. These are 3 there. Okay, so this is the Haber process. Now that's supposed to be a equilibrium array. For Kp, all of these are gases. And what Kp is Kp's equilibrium constant. We're just using it in partial pressures. So say, for example, we're making more products than reactant, Kp will be over here. If we're making more reactant than product, Kp will be over here. Kp is simply the equilibrium constant when we have gases instead of concentrations. And a mole fraction is the number of moles of gas in that mixture. So, for example, those are the approximate molar proportions of air. Those are the approximate molar proportions in air. We have 78% of N2, 21% of oxygen, and 1% of other gases. To calculate the mole fractions of these, the mole fraction of N2 will be 78, and then we're over 100 because that's the total number of moles. The mole fraction of O2 would be 21 over 100, and the mole fraction of the other gases would be 1 over 100. So they will all add up to the total pressure, your total number of moles, sorry, which is 100 in the end. So, in order to work out the partial pressure, we use that mole fraction. The partial pressure is the mole fraction of the gas times by the total pressure, because all of the partial pressures of a gas make up the total pressure. So, our box with like oxygen and hydrogen stuff in it, this might make up 10 pascals of pressure. Then the CO2 might make up 2 pascals of pressure. That's 10. That's 2. And then the nitrogen makes up 1 pascal of pressure. So our total pressure is 13 pascals. And then we are able then to work out the mole fraction, to work out the partial pressure. So we know that oxygen makes up 10 out of 13 of those pascals. So that is how much pressure it is exerting. There's lots of practice here. So we're coming towards the end now. I'm sorry we haven't been able to go over equilibrium constants in very much detail. It's very much been a whistle-stop tour, but hopefully you now understand what an equilibrium constant is, and you can understand that we have a Kc and a Kp. A Kc is for concentration and Kp is partial pressure of gases. So we're now just going to move on to kind of like the final aspect. You'll get sent this whole PowerPoint, so there are lots of practice questions in it which you can do in your own time. But we're now just going to move on to, oops. If I can get it to move back, oh dear. Now just going to move on to our little clinical skills corner to finish off the session. So can anyone put in the chat, do you know what this is? Does anyone know what this is? Oximeter. Yeah, that's really good. So This is called a pulse oximeter. Do you know what it does? They've just posted a feedback form in there if you could fill that out for me, and that would be great. But does anyone know what the pulse oximeter is? Yeah, that's brilliant. It measures your oxygen levels. So it's a little bit strange. You pop it on your finger. It's just a clip that you pop on your finger, and it tells you, as you can see here, the saturations of oxygen in your blood. Now, ideally, you want to be kind of above 95% oxygen saturations in your blood, but there are some circumstances in which when people are unwell, that it might not be that high. It also measures your heart rate, which you can see here. This person's heart rate is 73 beats per minute at the moment. But how does a pulse oximeter work? How can it tell all of that just from looking at your finger? Well, what happens is it shines light through your finger. And depending on the amount of light that's reflected and absorbed, it knows how much of your blood is saturated with oxygen. So it is very clever. It's very clever indeed. And it's a key tool in hospital. I'm currently placed on a respiratory ward. So this is obviously there's oxygen saturations are a key finding in what's going on with a patient, especially when they're obviously having respiratory trouble. So does anyone have any idea why someone's oxygen saturations might be lower than required? What might be going on with a person that means that their oxygen levels are a bit lower than required? Yeah, smoke inhalation. I hadn't really thought about that one, to be honest, but yeah, I suppose if you're not actually getting enough oxygen in because you're inhaling smoke instead of, yeah, that's a good thought. That's an interesting one. You got any other ideas? So the ones that I've been thinking of are specific lung diseases. So if your lungs are become scarred or they aren't able to work as effectively as usual, you might have low oxygen saturations, and so you need to be given a bit more oxygen. I was thinking of diseases such as like COPD, where your lungs get scarred from smoking and things like that. And so you would need a lot more. Your lungs aren't able to kind of like absorb as much oxygen into the blood as they were previously able to. But yeah, it's just an interesting thing to think about. Pulse oximeters are used in hospitals every day. They're used as part of like doing OBS and things like that. When the nurses go around and do observations on patients, and the pulse oximeter is something they'll stick on their finger every time they do that. So it's a really important key piece of information used for healthcare professionals to have a look at. But yeah, that's all from me today then. Please remember to fill out the feedback form, which has been popped in the chat for you. I hope you've enjoyed it. Yeah, just let me know what you think went well and what needs to be improved so I can make this better for next time. Hope you guys have a good rest of your weekend. And yeah, hopefully see you again soon. Bye.